Welcome to Practical Networking, where I draw upon my experiences as a network engineer to demonstrate how you can solve real world business challenges. And in this scenario, we're going to assume the role of a network administrator who's operating within a 24/7 service provider environment. The carrier for one of the internet links into the data center notified you that they're performing maintenance that may disrupt your traffic, and your task is to evaluate how to minimize network disruptions to avoid service impact. BGP, or the Border Gateway Protocol, is used in large scale networks like the internet, and it facilitates the exchange of routing and reachability information between different autonomous systems. Companies will use BGP to peer with internet service providers, and in this video, I'm going to illustrate how we can use different BGP features to influence the preferred routing pathway. I want to note that for the purposes of this video, I'm going to assume that you have some working knowledge of BGP. If you'd like a BGP basics video, or if there's other technologies or scenarios that you'd like to see, let me know in the comment section below. Before we take a look at any of the configuration, let's first take a step back, review the architecture and the options that we have available to us. So in our environment here, I'm going to drag out 4 routers, and this is going to represent the logical pathway between the client and the server. And I'm also going to add a couple of servers as well, which will represent the endpoints that are communicating with each other. And we'll start putting some labels here. We'll say that this is router 1. We have router 2, router 3, and router 4. Router 3 and router 4 represent the ISPs. Router 1 will represent the services that we're hosting. And router 2 will represent, wrong color, the client that is trying to communicate to the services that we're hosting. And router 2 is peering with both ISPs, which is the same for router 1 as well. And there's a few things that we can do in this scenario. First, we could actually choose to do nothing. In a high availability design like this, you should already have failover baked into your configuration. We have 2 peerings to presumably 2 different internet service providers. You should already have failover so that if an internet service provider experiences an issue with maybe one of their cards, one of their routers, whatever it may be, your traffic will automatically fail over to another internet service provider that you have communication with. So this should be something that's happening by design automatically anyway. It shouldn't be needed for any level of work needing to be done on your side for failover to happen. It should just happen and it should just work. However, you may elect to take a more hands-on approach and be a bit more proactive. And in that case, there's a couple of things that we can do. One of the things that we could do is revoke the advertisement from the ISP link. So right now we have router 1 peering with router 3 and router 4, which we'll say are 2 different internet service providers. And what we can say for router 1 is, I'm not going to advertise my routes to router 3 anymore. So from a router 2 perspective, the only pathway that it really has is through router 4 to get to router 1. So that's one step that you can take to influence the way the clients are communicating with the servers or for the services that you're hosting. Now, the other thing that you can do is AS path prepending. And this is where the routes you're advertising, you make them look less attractive on one pathway compared to another pathway. So AS path in BGP is used typically for loop prevention. And the way that it works is whenever you have a BGP route that gets advertised to your peer, you're going to put your autonomous system value inside of that packet so that the peer knows where the packet originated from or what pathways the packet went through. So as a route is advertised from router 1 to router 4, for example, the AS path is just going to be 1. If router 1 is an autonomous system 1, that's all that router 4 will see. Now, when router 4 gets that packet, it'll add its own ASN value, so it'll look like this, and it'll advertise that down to router 2. So when router 2 gets that, it's going to see, okay, this was advertised to me from my peer in Autonomous System 4, and it originated from Autonomous System 1. And that's how this advertisement is going to look from a router 2 perspective through the router 4 pathway. And this is going to be very similar to what will be seen on the other pathway as well. However, it's going to have router 3's ASN. So it'll look like this. Sorry, wrong color again. It'll look like this from router 2's perspective. Now, what you can do in this scenario is make one pathway look worse. So, for example, if on our side, router 1 side, when I say our side, if I decided to put more than just one copy of my ASN in that advertisement down, it would look like this. So if I decided to put my value 3 times, advertise that down to router 3, which then advertises it to router 2 is going to see this right here for the pathway through router 3. And although the AS path is typically used for loop prevention, it's also a gauge in the BGP metrics for route path selection, where if I take a look at these two prefixes that get advertised to me, I'll see that going through the pathway of router 4, there appears to be less hops than going through router 3. It looks like a shorter path, a shorter distance to get to that destination. So naturally, router 2 is going to take the pathway through router 4 because it looks like, from an AS path perspective, it's going through less autonomous systems, and it should be, in theory, a shorter number of hops to get to that destination. Now, the other thing that we can do is use community tags. Now, community tags are something that you need to coordinate with your peer. You can't just put a community tag on a prefix in a BGP update and assume that will be accepted and acted upon. You need to have agreement and coordination with whoever your peer is to take certain actions when you tag a community onto a prefix. So if I take, for example, my prefix that I'm advertising to router 3, and I put this community tag on it. This is the formatting. The numbers are typically a little bit different, but you get the idea. When I send that over to router 3, we need to have an agreement that says something like, hey, if I send you this community tag, what I want you to do is do that AS path prepending that we were just talking about. So instead of it looking like 1, 1, 1, followed by a 3, instead of it looking like that, it's going to look like 1, 3, 3, 3. And this is what router 3 will advertise down to router 2. So in effect, the same functionality is occurring. However, the minor difference being is that we're now prepending with routers 3 ASN to achieve the same result, but we're using a different method, which would be community tagging. Now, the community tagging could also be leveraged to take other action as well. It doesn't have to be AS path prepending. You could manipulate things like local preference, which alters the outbound routing pathway that router 3 uses. So instead of it going through, for example, this pathway here, maybe there's, I don't know, another pathway that it can route through to reach router 1. That's something else that could be done as well. So again, there's many different applications, but it's just a way for you to have a tag put on a prefix, send that to a peer, and then have an agreement with how that peer is going to treat that traffic to achieve whatever your desired result is. So those are our options that we're going to go through. I'm going to start all these nodes up now. That way we can start configuring everything. It's going to take a minute for that to happen. So I'm going to pause this video here and we can go from there. Okay, so now we have all of our nodes set up and they're up and running. I'm going to go through the basic connectivity and initial setup so that we can shell into these devices from a secure CRT session. That way we don't have the slow console and the noisy messages and all that goes into that. There will be timestamps in this video, so if you want to skip this portion, feel free to do so. However, I'm going to walk through the setup so that you can understand what we're working with here. So we're going to add our links between the routers. and we'll make sure that they match on either end. So gig 1 to gig 1, so on and so forth, just to make it nice and simple. And then we're going to connect router 1 to the server and router 2 to the client. Now, in addition to this, I'm going to add in an external connector through an unmanaged switch, which will allow me to connect my local home network to this lab environment. That way we can manage this from the local computer through a secure CRT session, and it's just a lot easier to deal with. So we're going to go ahead and add these links. And this will all be on Gig E4 just to make it consistent across. Hide that. Okay. So that's all done. So now we need to do the initial setup. So we'll start loading some consoles here. So we have router 1, router 2, router 3, router 4. Then we have the server, and we have the client as well. So here are all those terminals. So some of this is going to be a bit repetitive. I apologize in advance, but it's nature of the beast. So we're going to go into enable mode first, and then configuration mode. We're going to set the host name to router 1. And then we're going to set the AAA new model, followed by the username and the password. So username Cisco, password Cisco. Privilege 15 is just the access level, allowing us to make any changes to the device that we want, kind of like a root privilege if you want to think about it that way. And then we have to configure the domain name, and this is going to allow us to generate a pair of crypto keys, which will be used for the SSH connection. So we'll set that as cisco.com. We're going to set the enable password to Cisco because when you first log into the device, you get dropped into a shell that doesn't really allow you to do much. You have to go into enable mode or privilege exec mode. And to do that, you need to enter in a password. So like I said, this will be Cisco. And then we're going to go to the VTY line, which is used for line VTY04, which is used for either SSH or secure shell access, so remote access to the device over one of those two protocols. I'm going to just set this for SSH, and then I'm going to set the exact timeout to be 60 minutes. That way, if we're not doing anything in a terminal for a little bit, it won't just log us out. It'll give us a little bit more time. And then we're going to generate our crypto key. So we'll do crypto key generate, RSA modulus 2048. And this is what actually generates our keys, our RSA keys. That way we can SSH into the device. So that's done there. And we get to do it all over again. Actually, I'm going to see if I could just copy this from the other config here. There's no clean way to do it. Okay, so that's handled for those routers. In terms of the generic SSH configuration. However, we do need to add in some IP configuration as well as some routing so that we can route between these routers and the local network. So we're going to go to interface 4. We're going to set the IP address of 192.168.8.1. So my logic for this is that 192.168.8 is the local lab network in my home environment. And then the last octet, the 1, is going to be whatever the value is for the router. So 1 for router 1, 2 for router 2, so on and so forth. I'm going to enable that interface. And then we need to configure a route so that my computer can reach my lab network because they're on 2 different subnets. So we're going to say IP address, or I'm sorry, IP route of 192.168. And I'm just going to add in a /16 route here. And it's going to go to the local gateway. And let's go ahead and do that for router 2 as well. Oh, did I no shut that? Yeah, I did. Okay. Okay, so that is done for those devices. And we can also test this out. So if I pull up a command prompt here, we'll go here. We should now have this reachability. So ping 192.168.8.2, for example. That should be working. And it's making a liar of me. So let's see. All right. Well, it is up. Did I power this up? Links. Yep. Linked up. Okay, so that's the problem right here. This is set up as a NAT device, which it should be set as a bridge. So that's my fault. Let me go ahead and manipulate this. I gotta wipe it. We'll set this as a bridge. Start. And that should fix that problem. So that's my fault. Okay. So now we can move on to some server configuration. So let's go ahead and do that real quick while that's still working. So this is an Ubuntu virtual machine. So of course this is going to be configured a bit different. Usually under Etsy NetPlan, there is a cloud.init file, which is what we have here. And we're going to have to invoke root to manipulate this file. But we're going to go inside of here and we're going to change a few things. So right now we're only worried about the management access. So that's what we're going to, this is bugging out. So let me just re-enter it. There we go. What's the deal with this? This is another reason I don't like the console. It kind of gets weird sometimes. Okay, so now this is better. Okay, so we're going to go inside of here and set ENS3, which is our interface to that local network connection. So DHCP is going to be set to false. we're going to set the address, which is addresses, kind of confusing, but that's just the way they term it. 192.168.8.6 is what this will be. And we're going to set the gateway to 192.168.8.254. And then we have to do sudo netplan apply for these changes to take effect. And then if we do IP route show, we'll see that these are the routes that we currently have. So we have a default route through the local interface, which is good. That's exactly what we need. So if we ping 192.168.8.254, we have that connectivity. So let's go ahead and do this over to the client as well. Cisco. That's a net plan. Manipulate the cloud init file. ENS3 is going to be DHCP version 4 of false. Addresses for the client will be 192. Sorry, I forgot the brackets. 192.168.8.5/24. And the default gateway will be 192.168.8.254. Sudo netplan apply. Okay, so if we now go back to the command line interface, we now can ping to 8.1, 8.2, 8.3, 8.4. Let's see, we don't have any connectivity to 8.5. So that's kind of odd. We'll have to take a look at that and see what's going on there. Oh, there we go. Just came up. And 8.6. Okay, so we should have all the connectivity that we need. Now, if we pull in secure CRT and we'll do a connection. So hostname 192.168.8.1 with the username of Cisco. This should be router 1. So now we're inside router 1. And we'll just kind of do this as we go down. So we got router 2. Router 3. Router 4. Okay. Perfect. Okay. So we have all that connectivity that we need. So that's great. The only thing I'm going to do here is I'm just going to manipulate the host name so that it reflects either client or server. So we're going to say hostname server. Sudo hostname client. Just so it reflects within the shell. That way we know what device for sure that we're within and that we're manipulating. So if we exit and then go back into the device, now we'll see that this is the server. And this is the client. So we know exactly what device that we're in for the servers and the clients. So now we have management access to these devices, and we can proceed with finishing out the configuration. So this will be a bit easier now that we're not working through the console, which is a bit slower. So first we need to set up IP addressing between all the routers. So let's go ahead and do that. So for router 1, we're going to go into interface gig 1. So actually what we're going to do before we do anything else is we're going to run CDP or CDP run, just so we can see from a link perspective what device we are connecting to. Sometimes it's hard to remember. And it'll make things a little bit easier. Do show CDP neighbor. So even though CDP is running, we're not getting any entries, which is odd. Okay, well, the interfaces are down, so duh, that kind of makes sense. So we'll do interface range, gig 1 through 4, no shut. And what's kind of nice here is we just copy this over. It's actually an easier way to do this by using tab groups, but that's fine. So show IP interface brief. Okay, up and up. Up, up. All right, so we're up on all the interfaces. We should have something now, which we don't. So that's really weird. Okay. So this is what we'll do. So we'll group these devices together, which also groups these servers together. So maybe I won't do that. But you could actually run these devices within like a tab group and then issue one command that goes to all of them, which is kind of nice, but can be problematic if you're not paying attention. So let's instead do run LLDP or LLDP run, and we'll see if we get any output using this. Okay, so now we get output. I don't know why CDP isn't working, but LLDP for the win. So we know that from port 1, we're connecting to router 4, and port 2, we're connecting to router 3. So this is the general scheming of the IP addressing that we're going to use. We're always going to be looking from the perspective of either router 1 or router 2 when we're doing the IP addressing. And the third octet is going to be the corresponding peer followed by the device. So for example, if we're talking about router 1 to router 3, the IP is going to be 10.1.3.1. So router 1 to router 3, and then this IP belongs to router 1. And you'll kind of see what this looks like here in a minute to kind of make sense of it all. So if we go into interface gig 1, this one connects to router 4. So the IP address is going to be 10.1.4.1 because we're connecting router 1 to router 4, and this host is router 1. So if we go into interface gig 2, which connects to router 3, that IP address is going to be 10.1.3.1. Now for the gig 3 interface that's connected to the server, what we're going to do is we're going to set that as IP address 10.10.10.1. So this is our IP scheme here. So let's go to router 2 and let's do the same thing. So interface gig 1. First, let's take a look. Do show LLDP neighbors. So gig 1 is going to router 3. So IP address is going to be from router 2 to router 3. So that's 10.2.3.2. So interface gig 2 will then be 10.2.4.2. And then again, we have a server connecting to this device. So interface gig 3, that IP address is going to be 10.10.20.1. So anything that's 10.10 is going to be the server range. So 20 is just going to be because router 2, and then 10.10.10 is router 1, right? All right, so that handles for router 2. Now we need to do router 3 and router 4. So interface gig 1 for router 3, if we do show LODP neighbors, we have gig 1 going to router 2, gig 2 going to router 1. So for router 3, this is going to be IP address of 10.2.3.3. So again, link from router 2 to router 3, and I am router 3. And then interface gig 2 is going to be the IP address of 10.1.3.3. Hopefully the IP address scheme kind of makes sense. It was the best way that I could think of to represent the connectivity and for it to make sense. Because this is what we're going to see when we look at some of the peering. So it's helpful to have some scheme that sort of makes sense in your mind. So interface gig 1 for router 4 do show LOTP neighbor. We have gig 1 connecting to router 1, so the IP address is going to be 10.1.4.4. And it would help if I put a mask. Then interface gig 2 is going to be IP address of 10.2.4.4. Okay. So that's all configured, and that looks good there. Now, the only thing that we didn't do is finish the setup on the server side. So there are some additional things that need to be done there so that we could validate connectivity up to the local between the servers and the routers, or the client and the router. So when we go back and we take a look at what's inside of here, we can get rid of this pane now. So we finished this configuration here for all the routers and the basic IP addressing. We don't have the connectivity here between the client and the router, or the server and the router. So if we go back and we take a look at this configuration here, we could actually test and validate that some of this is working. So for example, if we ping 10.1.4.4, we see now this is working. So the first one is going to fail because there's no ARP entry. It has to try to send an ARP request to gather the layer 2 MAC address so it can start pinging across from a layer 3 perspective. That's why the first ping fails. That's completely expected and normal. Because if we do like a show ARP, you can see here the IP addresses that we have here and the interfaces that we have. So we can see, for example, we don't have an entry yet for 10.1.3.3, which is connecting off of gig 2. So we don't have that here yet. So if we do ping 10.1.3.3, we can now see that connectivity is working. And then corresponding, we'll look at router 2 as well. So we should be able to ping 10.2.3.3, which now that's working. And then 10.2.4.4. And that's working as well. So all that is working. However, you'll notice that pings to say 10.10.20.20 is not working because we didn't assign that IP yet, right? So let's go ahead and do that. So if we go, where are we at? We're at the client. So we'll start off here first. So change Etsy netplan. Sudo vi 50. Okay. So we'll go inside of here, and this is where we're going to set the parameters. Instead of relying on the router to hand out a DHCP address, whenever you have a server, it's always preferred to set the value yourself manually. So we'll go ahead and do that. We're going to set the addresses to 190. Sorry, not 192. So 10.10. So this is the client 10.10.20.20/24. Then we're going to save that for the gateway, we're going to use 10.10.20.1. Now for this to take effect again, sudo netplan apply. Okay, so now if we try to ping 10.10.20.1, we can now ping our gateway. So again, that's now working. So we'll do IP route show real quick. Just take a look at that. All right, so that looks good there. Perfect. So now we just need to do the server side. So Etsy netplan. We'll do the same thing here. So let's go in. We're going to set the DHCP to false. And we're going to say addresses is going to be 10.10.10.10/24. Gateway 4 is 10.10.10.1. Let's see. And that was for the client. The client's connecting to router 2. So to do all right. So that's working as to be expected. Okay. So this is the basic setup that we have now completed. So if we go back and we look at this environment here, we now have complete reachability through the secure shell environment to all the devices here. We have all the basic IP connectivity that we need. Next, we're going to start looking at the BGP configuration, setting all that up. And then from there, we can get into how we're going to manipulate the values, how we can manipulate the failure. So let's go ahead and set that up. So if we go into router 1, we could do router BGP1, which will start our instance for BGP with the ASN of 1. And then we're going to say that we're going to advertise the network of 10.10 with a mask of this. And then our neighbor is going to be 10.1.3.3. Their remote autonomous system is going to be 3 because they're router 3. And then we're going to have another neighbor of 10.1.4.4, remote AS of 4. Router 2, we're going to have router BGP2, and this is going to be advertising the network of 10.10.20.0. I forgot the mask keyword. And we have the neighbor of 10.2.3.3. Remote autonomous system is 3. And then we have a neighbor of 10.2.4.4. Autonomous system 4. So if we take a look at router 3, we're going to have router BGP 3. Our neighbor is going to be 10.1.3.1. Remote AS of 1. Then we have another neighbor of 10.2.3.2, remote autonomous system of 2. And for this router, we're going to do something a little bit different because this is the internet service provider router. Typically, there is a prefix list filter that gets applied for any peer so that you don't try to advertise routes that belong to somebody else. This is a very common thing that gets done. So that's what we're going to do here as well to make sure that there's no weird behaviors that may occur. So for the neighbor of 10.1.3.1, we're going to apply the prefix list of router 1 in the inbound direction. And for neighbor 10.2.3.2, we're going to do the same thing. Router 2 in. And then what we're going to do is we're going to set up the prefix list. So IP prefix list router 1. sequence. I'm just going to sequence it out. 5 deny 10.10.20.0. We don't want that, but we do want to permit 10.10.10.0. Now, on the opposite side, we want to do a prefix list for router 2 where we deny 10.10.10.0 and we want to permit 10.10.20. So that's set for router 3. Now, router 4, we're going to do the same thing basically. So, router BGP 4. And for this one, we're going to have neighbor of 10.1.4.1, remote autonomous system of 1, neighbor 10.2.4.2, remote of 2. And we're going to apply a prefix list, just like we did before. Router 1 in, and then 10.2.4.2, router 2 in. And we're going to set up our prefix list just like we did before. So we're going to do sequence 5, deny 10.10.20.0. Permit. Oh, sorry. Same sequence number. Perfect. And so then we'll do the same thing. IP prefix list of router 2, sequence 5, deny 10.10.10.0/24, sequence 10, permit 20. So if we take a look at BGP, so we can see that for router 4, we have our peerings, we have our prefix list, and our prefix list either allow or deny based upon where the route should be coming from. So show IP BGP summary. We have our peers up. And we have our peers up. Okay. So that all looks good. All right, very good. So we see that we now have all the BGP peering, we have reachability. So now we're done with the initial setup. We can move to the different options that we have available to us in terms of the failover options. So previously we went over that there's a couple of failover options that we have. And the first thing that we actually discussed was not doing anything at all and allowing the failover to happen naturally. So for this option, we're going to go through that real quick and kind of look at what are the issues that could potentially pop up depending upon your configuration. So if we take a look at the client and the server, so we have these Ubuntu devices where they're going to act as the endpoints for the communication. So the device here has the IP address of 10.10.20.20. This is the client, and it needs to reach a server at 10.10.10.10, which we currently have that reachability for, right? So right now, let's take a look at how this device is connecting to that remote server. So there's actually a few different ways. We could do a trace route, which we don't have that trace route utility. So that's okay. We'll just take a look at the routing. So if we take a look at the router of the client, which is router 2, and we check out the routing table, so we could look at show IP route, for example, and we'll just filter this a little bit further. We can see here that we're going through router 3. And we could also see if we look at the BGP table, so show IP BGP, we are getting 10.10 from router 3 as well as router 4. And you can see the autonomous system pathway here that we were talking about before. So it originated in ASN1, ASN3 then propagated that route to us, which is now what we received. And we see the same thing for router 4 here as well. So BGP has already selected a best path available. There's actually two pathways available for this same route, one through router 3, one through router 4. And currently we're taking the router 3 pathway. So what happens if we don't have reachability to that server through that router 3 pathway anymore? So if we go to router 1, which is where the server is located, the server attaches to this router, and we do show LLDP neighbors, we are connecting to router 3 through interface gig 2. So again, the client router is routing through router 3 to get to router 1. So this is the pathway we need to investigate if there's any problem with us doing nothing at all and a failure were to occur. So if we go to the pathway between router 1 and router 3, what happens if we do something like shut down this interface? So if we do interface gig 2 and say we shut it down, what happens? All of a sudden we start losing pings. So if you look originally, we were just chugging along, no problems at all. And then now we can see that the sequence number for every one of these ICMP requests, we just stopped completely at sequence 110. We're not receiving any pings. So let's take a look here. So show IP interface brief, we can see that the interface is administratively down. Show IP BGP summary, we can see that the BGP peering is down. So let's take a look at router 3. Show IP interface brief, we see that the interface is up. So when we take a look at router 3 from its perspective, the peering is still up and the peering is still valid. And this can happen for a number of reasons, but most commonly is just because you have router 1 and router 3 connecting to each other in a logical manner, point to point, it doesn't mean physically that the pathway is directly between router 1 and router 3. So as we look at it on this topology here, it seems like there's a single cable going from router 1 to router 3. And a lot of the times that's not the case. There's devices in between that we may not necessarily know or even really care about, but are along the physical pathway. There may be a switch or something along those lines where even though you shut down the interface on your side, for example, it doesn't necessarily mean that the other side is going to see that loss of the layer 1 pathway. And it may not register yet that this is no longer a valid pathway because of the default BGP timers. So by default, BGP is sending keep alives every 60 seconds, and a peer is only considered dead after 3 missed keep alive exchanges. So you basically have to wait 3 minutes for that dead peer detection to occur. And then once it does, then you'll see that the peering gets dropped. And at that point, the pings will start passing through the alternative pathway. But this is this is to illustrate that by taking no action at all, you could still run into an impact under certain conditions. Now, usually the default BGP peer timers are not used. Usually they're a bit more aggressive where the hello is set to 3 and the dead timers are set to 9. But as you can see, even in that case, you're still going to have a couple of packets that get missed. Certainly not as an extended downtime as what we're seeing here, but of course, it's going to result in some sort of impact. And then if we go back here, we can see that now the server has started to ping again because router 3 is now recognizing that this is a down peer as of 18 seconds ago. And we can see that from a router 2 pathway, it is now starting to take the pathway through router 4. So all in all, we had about 51% packet loss. We transmitted 286 and only 138 was received during that time period. So now we're going to take a look at the other option that we had available to us, which was revoking the advertisement from the ISP link and forcing traffic to go back around the other pathway that's available. So first we're going to go back into here and turn back up this interface. So interface gig 2, no shut. All All right, so that's up. BGP should be coming back up within the next couple of seconds, which it just did. Okay. So BGP is back up. And so let's take a look at the pathway that we're taking from a router 2 perspective. So if we look back here, we can see that we stuck with the router 4 pathway. Now that we have restored connectivity, we see that we now have 2 available pathways that we could potentially take. However, router 4 is now the preferred pathway with the recent change that we made. However, we do now have this as a secondary pathway through router 3. At this point, what we're going to do from a router 1 perspective is retract our advertisements to router 4, which should then force router 2 to start taking the pathway through router 3. So like before, we're going to go to the client and we're just going to start our ping and we're going to let that run. And then we're going to go to router 1 and we're going to retract our advertisements to router 4. So the way that we're going to do this is by using a prefix list. So what we're going to do is go into our BGP instance, and we're going to say for neighbor 10.1.4.4, which is router 4, we're going to apply the prefix list of R4 in the outbound direction. And then what we're going to do is create our prefix list called router 4, and we're going to insert a deny statement for 10.10.10.0. Now, if we take a look at router 2, we'll see that nothing changed. And this is because BGP updates aren't sent out immediately. They occur on a cadence, I believe it's like every 30 seconds or so. So what we can kind of do to kick this along is if we do a clear IP BGP followed by the peer, we could do a soft out. And basically what this does is it triggers the BGP process to recalculate the logic that's applied to it and push out an update for the new rules that you just assigned. So now if we take a look at router 2, we're going to see that we no longer have a pathway through router 4, and now we're taking a pathway through router 3. And if we take a look at our device during this time, we could see that we're still pinging. So compared to the previous scenario, we really didn't see any extended period of drops. We actually saw no drops, so 100 packets sent and 100 were received. We actually didn't lose any during this translation. During this transition from one pathway to another, because router 2 always had 2 pathways available to it. It already knew that there's another way that I can get to this network. It was already baked into the BGP table, so it was able to seamlessly flip from one pathway to another. So if we take a look from a router 4 perspective, before we were seeing that to the router 1 peer, we were getting a prefix, but now we're not getting a prefix at all. So this shows that we effectively have seamless failover in terms of using the prefix list method. So now we're going to take a look at the outbound prepend method, but first we're going to just undo what we did before. So if we do show run section BGP, and we'll just say no to this, that takes that out. And then we'll say no prefix list. And we'll reapply that. And now we have our pathway back. Okay. So we're back to where we were. Now, the other way that we spoke about being able to manipulate the routing is to make routes look less attractive on one pathway compared to another. So right now we see that for router 2, it's now back to using the pathway through router 3, through that ISP, right? So what if we wanted to manipulate that pathway to make it look worse than what it really is, so that we can influence the routing of router 2 to router 1? So what would that look like? Let's go back and put our pings in place so we can see if there's any impact and how that would look. So we have to go to router 1 and look at the peering to router 3. So what we're going to do here is for this, we're going to need to combine a prefix list and a route map. So a route map is going to reference the prefix list that has the IP address. And then we're going to say, if this condition matches, take this action, which is issuing a prepend. So from router 2, we're using router 3. So we're going to say IP prefix list router 3 sequence 5 permit 10.10.10.0. So notice we're issuing a permit here because we want to match the condition. We want to match that specific prefix. Before, we were issuing a deny because we wanted to filter or remove that prefix from being advertised. So in this case, we still want to advertise the prefix, but we want to make it look worse from an AS path perspective than the other route that we're advertising to our other peer. So we're matching it with a permit statement for this. And what we're then going to do is say route map, and we'll just say R3 peer, just to give it a slightly different name, permit 10, and we're going to match the IP address of prefix list R3. And then what we're going to do is set AS path prepend 1.1.1, not 1, 11111, right? So then we're going to go into our BGP instance and say neighbor 10.1.3.3. We're going to apply a route map of R3 peer in the outbound direction. And again, to kind of kick this over, because if we go back and we look at this, it doesn't really look like much has really changed. We're going to go ahead and do clear IP BGP 10.1.3.3 soft out. So let's take a look at router 2. So we can see here that our AS path has changed dramatically. So this pathway through router 3 looks way different than it does through router 4. And previously, if we take a look at the BGP table, we can see that we had this little caret here, which indicates that this is the best available pathway. And that was set to router 3 because all things considered equal, this was the better pathway. However, we can now see that because we have a really heavy AS path here through router 3, the best pathway has now switched to router 4. So there's now been a convergence of the routing table for router 2, taking the pathway now through router 4 to reach router 1. And if we go back to our client, which has been communicating with our server this entire time, we can see here that we haven't lost any packets. Same thing like before, 207 transmitted, 207 received. So now we're going to talk about our final option that we have here, which was using community tags to have this performed on our behalf by our peering partner. So let's go back into router 1, and we're just going to roll back the configuration that we applied. So router BGP 1, no neighbor 10.1.4.4. Sorry, no, it was 3.3 route map. Show run section BGP. So that's now gone. So we could also take away the prefix list as well, just to be super diligent here. And we'll take away the route map. Okay. So now we can see that the weighting has returned to normal and everything looks good here. So we could actually have our peer do this on our behalf if we wanted to. And this is how we would set something like that up. So from a router 2 perspective, we're routing through now router 4. So if we want to do something like this with router 4, it would look like this. First, on router 1 side, we need to set the community, advertise that, and then on router 4, we need to take action on that community. So it's very similar to what we just did before. We're going to make our prefix list. So IP prefix list this time will be router 4, sequence 5, permit 10.10.10.0/24. And then we're going to configure our route map of router 4 peer, match IP address of prefix list router 4. And this time we're going to set the community of this 1:1. And then we're going to do, under our BGP instance, neighbor of 10.1.4.4 route map R4 peer out. Additionally, we're going to need to provide the send community configuration. So this is actually going to send the community. The first part that we did for the route map is match the IP prefix, take an action, which is setting the community, but you have to configure send community on your neighbor to actually force the router to configure the router to send that community to your peer. So now that's done, we'll do clear IP BGP soft out. And then what we'll do is we'll go to router 4 and in this configuration, we need to do a couple of things. So first we have to define the community. So IP community list 1 permit 1.1. So this is kind of like an access list, a numerical access list, right? Where you define the list value, which in this case is 1, and then the actual community itself, which is 1:1. And then what we're going to do is a route map of R1 peer, and we're going to match community 1, and then we're going to say set AS path prepend. Now, this time we're going to use our ASN value. You always prepend with your own value, not another provider's. And then we're going to go into our BGP instance, and we're going to say neighbor of 10.1.4.1. We're going to apply the route map of R1 peer in the inbound direction. So if we do clear IP BGP soft in, because we're recalculating in the inbound direction the logic that we just applied. Do the same thing here as well. So we can now see that we flipped. Previously, we were routing through router 4. Now we are routing through router 3. And we can see here on the router 4 pathway, instead of prepending with a bunch of 1s from ASN 1, we're now prepending a bunch of 4s from the upstream ISP. And again, if we take a look at the client, the continuous pings that have been happening towards the server during this time, we didn't lose any packets. So this is how you can use community tags in coordination with your peer to manipulate the behavior of inbound traffic routing into your environment.